Hi everybody, I'm Mariano Scazzariello and I'm going to present Megalos, a scalable architecture for the virtualization of network scenarios. This is a joint work with Ariemma, Battista and Patrignani. The goal of the work is to create a virtual network scenario composed by devices represented by interconnected containers. A container implements a virtual device that can be simple as an atomic network function or complex as a fully fledged router. A virtual device is mainly composed by a virtual CPU with RAM and a virtual disk. Each container has several layer 2 interfaces, and each one is assigned to exactly one virtual LAN. Conversely, a virtual LAN can be connected to several interfaces. Virtual LANs have further requirements. The traffic between interfaces of a certain virtual LAN is kept separated from any other LAN, from the cluster traffic and from the internet traffic. Also, the packet sent by an interface must be received by the destination interface with no modification. We also want to allow hybrid network scenarios, which means that a part of the network is virtualized, while the remaining part can consist of physical devices and LANs. The integration between two parts of the network should be achieved with minimal configuration. The main goal is to create a scalable architecture which is capable of run on a cluster of nodes. Cluster nodes can be located anywhere on the internet, and each virtual device is allocated to a specific node of the cluster. The architecture should be also compliant with ETSI NFV standard. There are solutions that can partially meet these requirements. Some of them are able to emulate arbitrary network topologies and have a full protocol stack emulation. However, they are single host, so they don't scale up. Other solutions are distributed network emulation systems, which allow to distribute the workload between nodes, but they rely on virtual machines which are not capable to scale up due to their resources usage. Moreover, they're not compliant to ETSI NFV standard. On the other hand, a wide range of ETSI NFV compliant orchestrators is available in the industry. These orchestrators are also scalable and distributed, since they share the workload between different nodes. However, their network model is based on the VNF forwarding graph, and so they could not provide a full network protocol stack. So we present our Megalos architecture, which is compliant to ETSI NFV, even if not all the layers are needed by Megalos. First of all, the ETSI NFV architecture is composed by an operations support system for managing network services and customers. The virtual network function layer is the component dedicated to VNFs. In Megalos, this is implemented using Docker containers. Network function virtualization infrastructure represents the physical hardware on which the VNFs are deployed into. Here, the virtual computing also relies on Docker containers, while the virtual storage module relies on Kubernetes volume drivers, and the virtual network is managed by a custom Megalos plugin. On the right of the picture, you can see the management and orchestration component that, as the name suggests, is responsible for the management and orchestration of the architecture. The management and orchestration module is divided into three functional blocks. The virtual infrastructure manager manages computing, networking, and storage resources, and for this we rely on Kubernetes. The VNF manager is responsible for the lifecycle management of VNFs, while the NFV orchestrator is responsible for orchestration and management of the software resources and of deploying network scenarios on the infrastructure. Both VNFM and NFVO are implemented using a custom module called Megalos Controller. Kubernetes is based on the master worker model. In this model, worker nodes are controlled by master nodes through a daemon. So, the role of a worker node is to deploy containers assigned by master nodes. On the other hand, master nodes do not execute containers, but manage worker nodes and check the state of the cluster. External applications like Megalos can only interact with the cluster through APIs that are exposed by the master node. As described previously, virtual LANs are used to connect several VNFs. Virtual LANs must be able to traverse the physical cluster network, that can be any layer 3 network. Moreover, the original packets sent by the VNF must not be modified and, in order to avoid flooding, must be received only by the worker node hosting the VNF destination of that packet. To do so, we encapsulate packets generated by VNFs into VXLAN frames. This standard is based on Mac-in-UDP encapsulation, so it is able to send Ethernet frames through an IP network, making them even capable of traversing NATs and L4 firewalls. This slide is about details of the VXLAN protocol, because many of you already know it, but somebody maybe not. Each virtual LAN is identified by a Virtual Network Identifier, the VNI. VNIs are numbers used to distinguish packets belonging to different LANs. A dedicated field for the VNI is included in the VXLAN packet. Each VNI is also associated to a multicast IP address. In this way, packets are only sent to the specific multicast group and not sent broadcast. Another very important component is the VXLAN tunnel endpoint, the VTEP. VTEPs are responsible to encapsulate Ethernet frames into VXLAN packets, tagged with the corresponding CNI. They can be seen like VPN terminators, so they are bound to a single VNI. Moreover, they can be geographically distributed because they rely on multicast IP addresses. Unfortunately, unless you use further encapsulation protocols, multicast IP packets do not traverse Internet. Even so, there could still be some flooding in the cluster network because VXLAN leverages on the flood and learn policy to discover local MAC addresses. So, to avoid that, we disabled the flood and learn policy and replaced it with EVPN BGP as control plane. This allows to announce local MAC addresses through BGP updates, this thanks to the BGP multi-protocol extension. Additionally, this option avoids the usage of multicast packets and relies only on unicast traffic, because through BGP, each VTEP knows the association between the MAC address and the IP of the VTEP that hosts that MAC address. To implement this solution, we should deploy full mesh BGP peerings between worker nodes, but this can still generate a lot of signaling traffic in the cluster network. To overcome full mesh peerings, we deploy a route reflector on the master node, so each worker node needs only to communicate with it instead of all the other worker nodes. Kubernetes configures container networks using Container Network Interface plugins, or CNI plugins. However, currently available plugins don't support combined usage of VXLAN and EVPN BGP. So, we developed a custom CNI called Megalos CNI that automatically configures VXLAN segments, assigning each virtual LAN to a different segment. To support EVPN BGP, we built a special container running the FRR routing suite and deployed it on each node of the cluster. This container is specifically configured as route reflector when deployed on the master node. Normally, each BGP peer should statically specify its neighbors in the configuration. In our solution, there is a Kubernetes listener in the route reflector that catches every event of addition and removal of a worker node and changes the BGP peerings accordingly. Now I'm going to explain with a little more detail how the Megalos CNI works. So let's take a simple network scenario with two VNFs connected by a virtual LAN. Imagine that we have a cluster with two worker nodes and each VNF is scheduled into a different worker node. When Megalos starts a network scenario, in order to make the networking part work, a VNI is generated and VTEPs associated to the VNI are created in the two worker nodes. Second, the containers are deployed and connected to the local VTEPs. After that, each VTEP learns the local MAC address that is also injected in the EVPN BGP control plane. So each BGP router announces that MAC address to the route reflector, and then the route reflector sends that announcement to the other BGP routers. Finally, each received address is installed into the VTEP, and so the network is now able to correctly route packets between the containers. We need to schedule containers in an optimal way in order to minimize the traffic between worker nodes. Since Kubernetes native scheduler only allows to balance the usage of CPU and RAM, we developed a custom topology-aware scheduler that computes an optimal placement for the VNFs in the cluster, based on the specific network scenario topology. This problem is known in literature as the k-balanced partitioning of a graph, which is an NP-hard problem. So, to compute the partitioning, we use some approximation algorithms like hierarchical clustering or spectral clustering. The computed placement is then passed to the Kubernetes native scheduler as node constraints. Megalos can be used to emulate large networks, such as Fat3 data centers or the whole Internet AES hierarchy. Moreover, it supports network composed by heterogeneous technologies and applications, such as DNS servers, web servers, SDN, or routing suites. With Megalos, it is also possible to smoothly migrate, in just one move, a physical network into a virtualized one. So, it is possible to transpose each physical device into its VNF counterpart without any changes in the configuration of the network. To assess the efficiency and effectiveness of Megalos, we performed several experiments. First of all, we measured the virtual LAN scalability. We were able to allocate 500,000 different virtual LANs distributed among 1,000 VNFs on a single worker node. If you try to project the results on a full cluster, Megalos could allocate up to 2 billion of virtual LANs. However, VXLAN supports only 16 million of segments, and so the maximum number of virtual LANs is capped to that limit. To ensure that the scalability goal is achieved, we deployed a virtual Fat3 topology consisting of about 2000 VNFs on a Kubernetes cluster composed by 50 cheap worker nodes. A weak point of distributed architectures is that they might introduce unnecessary latency. Hence, we performed tests to measure the impact of Megalos on the latency of the virtual network. At this scope, we realized a network scenario consisting of a chain of n plus 2 VNFs, where the first and the last VNFs of the chain are a client and a server. Also, we never scheduled two VNFs that are consecutive in the chain to the same worker node. We want to demonstrate that the Megalos architecture does not introduce any additional latency. So, we measured the latency of the physical network, in red in the figure, and the round trip time of the chain deployed using a single worker node, in blue in the figure. Summing those values, we obtained the green line, that is the round trip time between the client and the server in Megalos. In conclusion, Megalos can efficiently implement very large networks that contain several heterogeneous virtual network functions. Also, we demonstrated that combining VXLAN and EVPN BGP can manage a high number of virtual LANs with a small footprint in the cluster network. Moreover, since VXLAN is a state-of-the-art technology and is supported by physical routers, Megalos can easily integrate physical devices into its virtual LANs. As next steps, we want to add the support for Kubernetes high availability. This is currently unfeasible since the VPN BGP route reflector must be in the master node and cannot be replicated. To overcome this limitation, we need to design an election algorithm that automatically deploys the route reflector in a worker node. Doing this, we can also support Kubernetes instances available in the public clouds that do not allow to schedule containers on the master node. Another step forward could be to design a topology-aware Kubernetes native scheduler. Thank you for the attention.